My name is Caleb Harris, and this is my report for Lab 2 for Physics 2211, Motion of a Falling Object. The purpose of the falling motion lab was to compare real-world falling motion to two computational models, one including only gravity and one including gravity and drag. My real-world model was dropping a lacrosse ball. The gravitation-only computational model represents only gravity acting on the ball. This model is unrealistic as there are other forces acting on the falling object. The other model represents realistic falling motion since it includes gravity and drag. The equations to represent these models are the impulse equation and the position update equation. The main physics principle is Newton's second law of motion. The change in momentum equation, mass times change in velocity equals F net times delta t, is tied directly to the kinematic equation Vf is equal to V naught plus acceleration times time. Vf is the final velocity in meters per second, while V naught is the initial velocity also in meters per second. A represents acceleration in meters per second squared, and t represents time in seconds. Finally, Newton's second law of motion also plays a role, which is represented by the equation F is equal to mass times acceleration. F is force in newtons and m is mass in kilograms. The main result of the lab was that the ending change in position of the computational model, including gravity and force, is closer to the ending change in position of the experimental data. The system is a lacrosse ball, and the surroundings are everything else in the universe. The initial velocity is 0 meters per second in the x dimension, 0 meters per second in the y dimension, and 0 meters per second in the z dimension. The initial position of the ball is 0 meters in the x dimension and 0.002331 meters in the y dimension and 0 meters in the z dimensions. To grade the code for the gravity-only model, I first edited the mass and initial conditions to fit my object. Since the initial position of the y dimension was so small, I put it as 0 in GlowScript. Then, I used the momentum principle to get the velocity. I said it earlier, the impulse equation is change in momentum in kilograms times meter per second equals F net times delta t. The calculated velocity was used in the position update formula to find the position. The position update formula involved using velocity average to get an accurate prediction of the change in distance. The drag model was the same except for I included the proportionality constant, the square of the speed, and the force acting in the direction of supposed gravity. My B value was 0.0752, and this was acquired by running the code until it resembled my experimental data. The computational models were used to represent drag and a lack of drag. The main similarity is there is a present net force. There is net force in both models, so the ball's velocity changes. The main difference is that one model includes the gravitational force while the other includes gravity and drag. This observation relates to Newton's second law of motion, which states when the net force acts on an object, the object will accelerate in the direction of the net force. Gravitational net force close to the Earth is represented by mass times gravitational acceleration, which is represented by 9.8 meters per second squared. In one model, this is the only force acting on the ball. This is completely unrealistic as there are other forces like drag acting on falling objects. In the other model, there is gravity and drag. In the y dimension, the drag acts in the positive y direction while gravity works in the negative y direction. A possible source of error was that I might have exerted a force on the ball, preventing the ball from starting from rest. Even if I dropped the ball, my finger might have slightly pushed down on the ball, causing an initial velocity greater than 0. The model with drag represents terminal velocity because the net force has to be 0 at terminal velocity. Terminal velocity is the maximum velocity of a falling object in which the net force is 0 from gravity and drag canceling out. The terminal velocities would be the same no matter if the object was thrown versus dropped. However, the thrown object would reach terminal velocity sooner. The main difference is that the gravity-only model shows velocity increasing in magnitude forever, never reaching a terminal velocity. In the gravity and drag model, the velocity graph has a concave up behavior as the velocity plateaus. The gravity and drag model position is closer to the experiment position because it accounts for the proper net force, which is gravity and drag opposing each other in the y dimension. My object does not reach terminal velocity because it reaches the ground before the gravity and drag force can cancel each other out. The main models of the lab were Newton's second law of motion, the impulse equation, and position update formula.